probability, we need to understand things like random variables and sample spaces. And to understand these things, we need to understand terms like countably infinite and uncountably infinite, and so on and so forth. So our starting point in this course will be set cardinality. Okay, so to tell the story of probability from the very beginning, from the axioms of probability, we need first to understand the cardinality of sets. And the cardinality of a set is simply the number of elements in the set. So if you have a set composed of A, B, C, D, so that's a finite set. And it is clear that basically the cardinality of the set, the number of elements in the set, is equal to 4. We have 4 elements. And there are several notations for the cardinality of a set. Here I will use basically these 2 vertical bars. So if you have a set between the 2 vertical bars, then basically we are talking about the number of elements in the set. Okay. Now for finite sets, things seem like trivial. But the question is basically regarding the infinite sets. Okay, so those are interesting and they appear a lot in probability. And so what about infinite sets? Can we say that like all infinite sets are basically the same size? They all have the same number of elements, which is infinity, and that's it? Or the story is a bit more complicated, okay? So conventional or mainstream mathematics relies on the idea by mathematician Cantor, and this idea is that we say that 2 sets, and these 2 sets can be infinite, they have the same number of elements or the same cardinality if you can establish a one-to-one correspondence between the elements of the set, okay? So let's take these 2 sets. So this is the set of natural numbers, 1, 2, 3, and so on. And then the set of even positive integers, 2, 4, 6, and so on. So we have these 2 sets, okay? And now imagine this function, g of k is equal to 2k, where k is a natural number. So basically function g is a function that is defined with a domain that is the natural numbers, and it takes each natural number to another natural number, okay? And this natural number in the codomain is double, is 2 times the natural number in the domain. So 1 is mapped to 2, 2 is mapped to 4, 3 is mapped to 6, and so on. Okay. Now this function is a one-to-one correspondence in the sense that if I tell you what is 4 mapped to, you will automatically say, oh, 4 multiplied by 2, so 4 is mapped to 8. So 4 here goes to 8 here. Now, if I give you an element in this set, okay, an element in this set, which is NE, sorry, the even natural numbers or even positive integers, now you can know the element from the natural numbers that is mapped to this element. So for instance, if I tell you there is a number here, an even integer, which is 38. So 38 is associated with what element in the domain? So you say, okay, I will take 38 and divide by 2, okay, to get 19. And so basically it's 19. So each element in the domain is associated with an element in the codomain, and the opposite, mapping or a one-to-one function or correspondence. Because these 2 sets, we can have a one-to-one correspondence between their elements, then the sets are equicardinal. They have the same cardinality, the same number of elements. Okay, so again, this is a fundamental idea that if you want to compare sets, you want to compare the number of elements in 2 sets. If you can establish a one-to-one map between the elements in the two sets, then that's it. The two sets are said to be equinumerous or equicardinal. They have the same cardinality, the same number of elements. Okay, and now there is something here. Okay, I mean the idea seems to be very plausible. Okay, but note from our example there is something annoying about this idea, which is that the set of even natural numbers, which is this set, is a proper subset of this set. Okay, so NE is a proper subset of N, right? Every even natural number is a natural number, but of course there are natural numbers that are not even. You know, the odd natural numbers, 1, 3, 5, 7, and so forth. So in other words, despite the fact that this set is a proper subset of that set, despite this fact, because we can establish a one-to-one correspondence between them, they have the same cardinality, the same number of elements. Okay, and so there is a rule that if A is a subset of B, then the cardinality of A is less than or equal to the cardinality of B. But it may happen that one set is a proper subset of another set. Both are infinite sets. So one infinite set can be a proper subset of another infinite set, and yet they have the exact same cardinality. Sort of a counterintuitive result, because it tells you that in the world of infinity, the part can be put into a one-to-one correspondence with the whole, an idea that we do not see in real life, but it is there. Okay, so this is a surprising, sort of a surprising result, but this is what mainstream mathematics basically do when we talk about infinite sets. So two infinite sets are equinumerous, or they have the same number of elements if you have a one-to-one correspondence between their elements. And yes, it may happen that one of the sets is a proper subset of another. Okay, so you can, I mean, we will not go into details, but you can show that, for instance, the following sets, they have the same cardinality. The set of natural numbers, the set of integers, and note that all natural numbers are integers. Okay, despite this, they all have the same cardinality. And also the set of rational numbers, all fractions that are basically in the form of an integer divided by a non-zero integer, all the rational numbers, okay, basically they can be put into a one-to-one correspondence with the set of natural numbers. So you may think that this is like very far-fetched. So rational numbers are, they appear to be much more than the integers and the natural numbers. However, you can find a one-to-one map linking these two sets. So surprisingly, the cardinality is the same. The cardinality of the natural numbers is the same as the cardinality of the rational numbers. Okay, and this will be important when we talk about things like random variables and so on. And so all those sets, they have the same cardinality. We do not basically need to go into how actually to find the one-to-one correspondence between each pair of these two sets, but we will take this for granted, and basically the cardinality of the natural numbers and the sets that can be put into one-to-one correspondence with the natural numbers is denoted by Aleph note. Okay, so it is a funny N and then a note is 0 here. Okay, so sets that have this cardinality, they are called countably infinite sets. So any infinite set that can be put into one-to-one correspondence with the natural numbers, it is called countably infinite. So it is infinite, but it can be put into one-to-one correspondence with the counting numbers, the natural numbers, 1, 2, 3, and so on. Okay, so this is basically the countably infinite sets. But there are so many infinite sets. So do all of them share the same cardinality, or what is the story? Okay, so let's now go to the second part. Okay, so before proceeding to the second part, so do you hear me? Okay. Does anyone have any problem with the sound?
We can hear you.
Okay, great. Okay. So let me continue. Okay. Now let's go to another, basically bunch of sets. So for instance, we have the set of real numbers, very important for continuous random variables. We have the set of mixed numbers. We have basically the set basically representing the points in a plane. We have the irrational numbers. So those are the real numbers that cannot be represented by a fraction. Okay, so what about these sets? And what about the intervals? Okay, the intervals from A to B, and these intervals, they come in these four flavors. You have the closed interval, including A and B. You have the open interval without A and B, and then you can have B included, not A and the other case here. So what about those sets? So you can show, again, it may be surprising, but in the world of infinities, yes, the part can be put into one-to-one correspondence with the whole. So basically all the sets, all those guys, they can be put into one-to-one correspondence with one another. Okay, so according to Cantor's idea, they have the same cardinality, the exact same cardinality. Okay, and now the question becomes, but is this Aleph node? So those are also infinite sets, and you can show that basically there is a one-to-one correspondence between each pair of these two sets. But can you establish a one-to-one correspondence between one of those sets and the set of natural numbers? Okay, so do they have a cardinality Aleph node or something else? So now we will show that no, they have a cardinality that is strictly greater than Aleph node. Okay, so there is not, just one size for infinity. In fact, there is an infinite number of infinities. Okay, so let's see why, for example, those sets, they are not countably infinite. Okay, they have a cardinality that is greater than that of the natural numbers. Okay, so one of those sets, like R and C and R2, which is basically the 2D plane and so on, is the set of all 0, 1 infinite sequences. Okay, so basically what we will show that is this set. Okay, so this set, it has the same cardinality as any of those guys, again, because of this idea that you can establish a one-to-one correspondence between any of those sets and this set. So this is the set of all 0, 1 infinite sequences. Okay, so what we will show is that we will basically demonstrate that this set is strictly larger than the natural numbers. Okay, and so it is an infinite set with a cardinality that is not Aleph node. It is something that is greater, strictly greater than Aleph node. Okay, so here is the proof. The proof, by the way, is very important. It is a general idea called the diagonal argument or the diagonal proof, and it is used in a couple of places in mathematics and computer science. And here is the idea. It is, we will do proof by contradiction. So we will take the sequences of 0, 1 that are infinite. So one of those sequences is something like this: 0, 0, 0, 0 to infinite, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 0, 1, 1, 1, and so on. Those are those sequences. Okay, so we will assume basically that the set of binary sequences that are composed of 0 and 1, we will assume that this set actually is countably infinite. It can be put into one-to-one correspondence with the natural number. Okay, so what does this mean? It means that basically the elements, those sequences, each one of those sequences can be numbered. The sequences can be put a list, and this list can be numbered 1, 2, 3, 4. The first sequence, the second sequence, the third sequence, and so on. Okay, so we will assume, that basically the set of all infinite binary sequences can be put into one-to-one correspondence with the natural numbers. Okay, so basically the sequences can be put in a list, and this list can be like this. The first sequence, S1, S2, S3, S4. Each one of those guys is basically a string, an infinite string of zeros and ones. So here is the case sequence. I will call it S sub k. So here the subscript means basically the index of the sequence. And k is a natural number. Why k is a natural number? This is under our assumption that the sequences are actually countably infinite. So they can be indexed by the natural numbers. So there is a sequence sk where k is a natural number, and this sequence is composed of, basically bits. Each location, each position in the sequence is either 0 or 1. Okay, so sk1 is the first location in the sequence, or the first position, and it can be 0 or 1. sk2 is the second position, and so on and so forth. Okay, so those are binary sequences composed of, an infinite string of bits or positions, whatever you want to call them, and in each position you have 0 or 1. Okay, so there is some first sequence. Okay, so the first sequence can be, this one here, 0, 1, 0, 1, 0, 0, 0, 0, and so on. The second sequence can be like this. The third sequence can be maybe actually the all one sequence, and all of them are infinite sequences. So they do not stop. They simply extend to infinity. Okay, so again, why are we able to index the sequences using the natural numbers? We are able to do so not because this is true, but because we assume this to be true. We assume that basically we can have a one-to-one correspondence between the set of infinite binary sequences and the set of natural numbers. Okay. But now let's construct a sequence, a new sequence. Okay, a new binary sequence. Okay, so here is the way of construction. We will go to the first sequence. So we will construct a new sequence by doing the following procedure. We will go to the first sequence. Okay, so it has something in the first position. Its first bit is something. Here it is 0. Okay. So you take the complement. You take basically, if it's 0, you put 1. Okay, so my new sequence, I will put it in green. I will take 1. So if here is a 0, I put 1. If here were 1, I would put here basically 0. So basically, the general idea is that if you have here S11, your new sequence, the first bit in your new sequence will be S11 bar, which is 1 minus S11. So if S11 is 0, you put a 1. If it's 1, you put a 0. And so this will be the first bit in your new sequence. Okay, then you go and visit the second sequence. Okay, and specifically you take the second bit of the second sequence and you flip it. Okay, so the second bit of the second sequence here, it's 0, and so I will also put a 1 here. And then you go to the third sequence. Okay, and you see the bit here. The bit here is 1, so you flip it and it becomes 0. And you repeat this, and you can see why it's called the diagonal argument, because basically you move diagonally across the sequences. Basically, you take the first bit in the first sequence and flip it. You take the second bit in the second sequence and flip it. You take the third bit in the third sequence and flip it, and so on and so forth. And so you will construct a new sequence. Now, is this new sequence part of the family? Yes, because basically it will be an infinite sequence of zeros and ones. So basically this new sequence is basically a member of the set of infinite binary sequences. Okay, again by construction. We do not use anything other than 0 and 1. So basically, it is part of the set. It is an element in. So if the new sequence is an infinite binary sequence, then it is equal to S something, right? So this sequence must be some SM. Okay. It must be some SM. Where, you know, again, it must be maybe S subscript million, S subscript trillion, whatever. But it must be one of those sequences because it is an infinite binary sequence, and we assumed that we have a list, an exhaustive list of those infinite binary sequences. So our new sequence must be one of those guys. Which one? Is basically our new sequence, is it S1? Is our new sequence S1? No, because it differs from S1 at least in the first position. S1 has 0 in the first position. It's a 0 here, but our new sequence has a 1 here. It's not S1. Okay, it's S2. No, it's not S2 because S2 has a 0 in the second position, while our new sequence has 1 in the second position. So it may be S3. No, because S3 has 1 here, but our new sequence has a 0 here. So maybe it is S trillion. No, because remember how this new sequence was constructed. Basically, the nth bit in the new sequence, you go to the nth sequence and you take its nth bit and then you flip it. If it's a 0, you make it 1. If it's 1, you make it equal to 0. Right? So this means that our new sequence is not any of those sequences. So that's a contradiction. So the contradiction is that we assume that there is a one-to-one correspondence between the set of binary infinite sequences and the set of natural numbers. This allowed us to say that we can index the infinite binary sequences using the natural numbers. S1, we can say that we have a list S1, S2, S3, S4, and so on. Yet, we were able to construct an infinite binary sequence that is an infinite binary sequence, no doubt about this, but that is not in the list. Despite the assumption that the list is exhaustive, it basically includes all possible binary infinite sequences, okay? So that's a contradiction. Okay, so this is a contradiction, and it means that the elements of 0, 1 to infinity, which is basically the infinite binary sequences, this set cannot be exhausted by the natural numbers. We cannot index this set by the natural numbers. If you do so, you can construct basically the contradiction we mentioned, and hence our assumption is wrong. Basically, this set here, it has a cardinality that is strictly greater than Aleph node. This set here, if we want to index this set, we need to use something that is strictly larger than the set of natural numbers. Okay, so basically, this establishes that that infinity is not just one thing. So there is the infinity Aleph node, which is the cardinality of sets like natural numbers, integers, rational numbers, algebraic numbers, and so many other sets. All of those can be put into one-to-one correspondence with one another, and all of those have the cardinality Aleph node, and we call them countably infinite sets. But there are sets that basically like are real numbers, complex numbers, intervals, whether they are open or closed, half open, half closed, and so on, and the set of infinite binary sequences, all those sets, they have the same cardinality because, we didn't show this, but you can look it up or take it for granted. You can take any pair of those sets and find a one-to-one correspondence between the elements. So they have the same cardinality, which is C, which is called C, small c, but small c is strictly greater than Aleph node, and the diagonal argument showed this, that basically you cannot exhaust something like the set of infinite binary sequences using the natural numbers. So an infinite set whose cardinality is C or greater, so any set that is infinite and that has a cardinality that is strictly greater than the cardinality of the natural numbers, this set is called uncountably infinite. Okay, and so those basically terms will play an important role in classifying random variables, as we will see later, and actually sample spaces. Okay, so again, infinity is not just one thing. So there are countably infinite sets and there are uncountably infinite sets. Okay. Sampling space. So basically, probability, or formally we say probability space, is composed of three things. Okay, so something called the sampling space, and this will be my topic now. Then something else called the sigma algebra, and then there is the third component is the probability measure. Okay, so formally speaking, if we talk very formally about probability, then probability, or a probability space, it has three components: sample space, sigma algebra, and basically a probability measure. Okay, so sample space, omega, big omega, capital omega, the set of all possible outcomes of a random experiment. Okay, so you do an experiment and then you collect all possible outcomes of this experiment in one set, and this set is called the sample space, right? So if you throw two dice, okay, then what are the possibilities that you get? You may get 1, 1, or 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, and so on. So basically you get the numbers on the two dice, okay? And so you have a total of 36 possibilities. And so we can think that the experiment of throwing a dice, basically it's associated with a sample space that is finite, and it has a cardinality of 36. So we have 36 elements here. Now, suppose that you do an experiment in which you take a coin, you flip a coin, and you count the number of tosses until you get your first head. Okay, so you toss a coin, okay, you may get a head from the very beginning. So basically you need one toss and you have a head, that's it. Then you may get a tail and then a head. So you need two tosses till you get your first head. But you may get tail head, or tail head, or tail head, and so on. So basically the number of tosses needed so that you get your first head, it can be any natural number. Okay, so it can be 1 or 2 or 3 or 4 or 5 or a million. Yeah, I mean, it's very unlikely, but it may happen that you get 999,999 basically tails and then one head. Okay, it may happen. So basically, in this case, we say that our sample space is basically the natural numbers. It's an infinite sample space. Okay, and so the cardinality is Aleph node. Okay, it's a countably infinite set. Then in one experiment, you may be interested in choosing or picking a point between 0 and 1. between the interval on the real line between 0 and 1. So 0, 1, and 0 and 1 inclusive, and you want to pick a point here or there, okay? And so basically, you get any number between 0 and 1 inclusive, and so this is an interval. And remember, in the previous slide, we said that intervals on the real line, they have the same cardinality as the set of real numbers, okay? And so this cardinality is what is called C, small c, and small c is strictly greater than nth node, okay? So the moral of the story is that depending on your experiment, the sample space, which is the set of all possible outcomes of a random experiment, the sample space may be finite with a finite number of elements, or it may be countably infinite with a cardinality nth node, and this means that the set of possible outcomes can be put into one-to-one correspondence with the set of natural numbers, or basically the set can be uncountably infinite, which means that the number of elements in the sample space is strictly greater than the set of natural numbers. Okay, so we have the three possibilities, and this last possibility is quote unquote an evil one, and we will see it will you know, it causes problems, you know, if you try to do things, you know, in a non-rigorous way. So the elements of big omega, typically each element of big omega is denoted by small omega, and it's called an elementary outcome. Okay, so the set big omega, which is the sample space, any set, it has subsets. Okay, so we are typically interested in subsets of big omega, and those subsets are called events. So formally speaking, when we talk about event, when we say event in probability, we are talking about a subset of big omega, a subset of the sample space. Okay, so if you throw one dice, then big omega is basically the set 1, 2, 3, 4, 5, 6. Standard dice, okay? Now, you may be interested in getting an even number. So getting an even number, it means that you are interested in getting either 2 or 4 or 6, which is a subset of this big omega. You may be interested in getting a prime number, square number. You may be interested in getting something that is less than or equal to 4 or greater than or equal to 3, and so on. So typically, when we do those experiments, we are interested in events, subsets of big omega. And we are also typically interested in the complements. So you may ask yourself, will I get an even number or an odd number? Will I get basically a number that is 3 or less, or that is greater than 3? So typically when we do experiments, we are interested in the occurrence of an event or the non-occurrence of an event. So our interest typically involves the complements of some subsets of big omega, unions, intersections, and so on. And so probability basically is a very old science, right? It was made mathematically rigorous only at the beginning of the previous century, okay? But those who made it rigorous, specifically, you know, I will mention Kolmogorov, basically they made it rigorous based on knowledge, you know, so they did not invent probability. Probability was there, and they basically tried to make it you know, they tried to establish it on mathematically rigorous grounds, okay? So, so now you know, we have this concept of a sample space, the set of all possible outcomes of a random experiment. The subsets of the sample space, okay, are called events, and we are typically interested in those, some event and its complement may be the union of events, the intersection of events, and so on and so forth. The second component of a probability space is this thing called sigma algebra. So what is a sigma algebra or a sigma field? So a sigma algebra is basically a collection of subsets of some set. So you have a set, okay? And this set has subsets. Okay, so let's have a set. Okay, so this is set A, B, C. Okay, that's a set. So what are all possible subsets of this set? Okay, so empty set. It's always a subset of any set. Empty set. Fine. A set with one, with A, with B, with C, or you can take A with B, A with C, B with C, and A with B with C, like this. So those 8 sets are basically all possible subsets of this set. And you may know already that basically if you have a finite set with n elements, then the number of subsets is equal to 2 to the power small n. So if we have a set with 3 elements, like in our case here, then we have 8 possible subsets. So the sigma algebra is a selection of subsets. Okay, so a sigma algebra tells you you do not have to operate on all the subsets. You may just choose some of those subsets. But is our choice arbitrary? No. Our choice must be very specific and must obey 3 things. 1, you must choose the empty set. So for a collection of subsets to be called the sigma algebra, you must include in your collection of subsets, you must include the empty set. Number 2, if you include a subset, you must include its complement. You must include its complement. So for example, if you go to our example and say, okay, I will choose B, this subset, to be part of my collection. You need this as a part of your collection. Okay, then you are under obligation. If you are constructing a sigma algebra, you must choose the complement of this, which will be this guy here. The set containing the other elements in omega. So these two come together. In other words, if you choose one of them, you must choose the other. Okay, so the second property of a sigma algebra, it is closed under complementation, which means that if you choose a set, if you choose a subset, you need to choose the complement of that subset. Okay, so if you choose A, okay, which is a subset, you need to choose its complement. The third thing, if you choose a bunch of subsets and say, oh, I will take those guys in my sigma algebra, in my collection of subsets, then you will have also to include the finite or countably infinite union. Okay, so if A1 is a subset of big omega, A2 is a subset of big omega, A3 is a subset of big omega, and you take all those guys in the sigma algebra denoted by this scripted F, then the union must also be included. So in other words, let's go here. So if you decide, say, I will take this in F, okay, so I will take this, and I will take this in F. I will choose the singleton subset containing the element A and the subset containing the element C. Then you are under obligation to take AC, which is the union of these two guys. So if you take A and if you take C, there is no way you need to take their union. Okay, and so this is basically how we define the sigma algebra. And as we tell the story, you will understand why do we insist on these properties? So these properties are, they did not emerge in vacuum, okay? So they are important, okay, when we basically deal with probabilities, okay? So, now, if you know that these are the properties of a sigma algebra, what else do we know about a sigma algebra? Claim big omega itself, right? Any set is a subset of itself. Big omega itself is part of a sigma algebra. Why is this true? Why? So basically, there is no item here telling you that you should choose big omega, basically the set itself. Well, it is in these two guys taken together. So according to the first property of a sigma algebra, when you are constructing your sigma algebra, you need to have phi in the sigma algebra, in this collection of subsets. You need the empty set. But according to the second property, if you take a subset of big omega and include it in the sigma algebra, you also need to include the complement. So if you include phi, the empty set, you will need to include its complement, which is big omega. So actually, any sigma algebra will include the empty set and will include big omega. So those must be chosen in any sigma algebra to be a sigma algebra. Okay, so this is one thing. Another thing is that in the definition of a sigma algebra, we talked about union. So if we have, subsets that we include in our sigma algebra, then we also include their finite union if there is a finite number of those guys, or countably infinite union if there is a countably infinite number of those guys. What about intersection? Like, why specifically union? Why not intersection? Well, actually, we also have the intersection. It comes for free. We do not need to mention it explicitly. So let's try now to understand why, if A1, A2, A3 are part of the sigma algebra, then also the finite or countably infinite intersection is also part of the sigma algebra. Okay, so suppose that basically you have subsets of big omega, so each one of those guys is a subset of big omega, and you take them and you include them in your sigma algebra. Okay, then by the second property, if you include a subset, you are under obligation to include its complement. So if you include the subset A1, you will have to include A1 complement, A2, A2 complement, A3, A3 complement, and so on. Okay. And by the third property, if you have those guys included in the sigma algebra, then you should have their union. It must be part of the sigma algebra. Okay, so the union of those guys is part of the sigma algebra. But then we have Demorgans Nodes. So Demorgans Nodes tells you that if you have, actually it is general, it is for any collection of sets, even if uncountably infinite. If you have a collection of sets, okay, let's say that we will call them gamma, okay, gamma k complement, okay, then the union of the complements is exactly the same as you take the intersection, okay, of the guys and you complement the intersection. Okay, so this is Demorgans law. Okay, that basically the union of the complements is the complement of the intersections. So if this guy is in the F, then this guy is actually is basically the intersection. I is a natural number of AI, okay, all complement. So this is in F. So going from here to there is Demorgan. I mean, it's basically these two guys are the same. Okay. But if there is a subset that is included in the sigma algebra, then by the second property, we must include its complement. If you have something, a subset from big omega, and you take this subset in the sigma field or the sigma algebra, you have to also take its complement. So if this thing is in the sigma algebra, then its complement is also in the sigma algebra, and the complement of the complement is simply the intersection itself. So the intersection is also in the sigma algebra. Okay, so now we can say that the sigma algebra is basically a collection of subsets. You need to include the empty set. You need to include big omega. If you take a subset, you need to include its complement. If you take a bunch of subsets, you need to include unions and intersections. Okay, finite unions and finite intersections, and countably infinite unions, countably infinite intersections. Okay, so this is what constitutes a sigma algebra. Okay, so let's take example. Okay, so this is big omega. So it's a set, it's a finite set, and it has 4 elements. What are sigma algebras that can we define on this set? So again, what are the subsets of big omega? How many subsets do we have? It is a finite set with 4 elements, so it has 2 to the power 4, 16 subsets, and I think they are here. Okay, so those are the 16 subsets of big omega. They include the empty set, they include omega itself, and those other guys. Now, you may have a collection of subsets, and if this collection obeys those 3 properties, then we have a sigma algebra. Okay, so here is our first example of a sigma algebra. It's a trivial sigma algebra. You just choose the empty set and big omega. Okay, this is a sigma algebra. It's not interesting. It's not that useful. But you know, if you just choose these 2 guys, you indeed have a sigma algebra. Right? You have the empty set. You have the complement of the empty set, which is big omega. And basically, you have the union and intersection of these 2 sets. Their union is big omega, and it's there. And the intersection is the empty set, and it's there. So this is indeed a sigma algebra. It's a collection of subsets. So from the 16 subsets, we just use 2 of them, and you know, this selection is a sigma algebra. This selection, it obeys the properties of sigma algebras. Okay, so this is one. So what is another sigma algebra that is sort of obvious? You choose everything. So you choose the power set. So the power set is basically the set that contains all possible subsets. So in other words, your second possible sigma algebra is that you do not exclude any subset. You simply take all of them in your collection of subsets. Okay, and so you take the power set. Okay, and you can verify that everything is included. So you have basically, you know, you have the empty set. You have for any subset, you have its complement there. You have, if you take 2 or more of the guys, their intersection will be there, their union will be there, and so on. Okay, this is indeed a sigma algebra. And now, this is a sigma algebra that is a bit more interesting, because now this is not the trivial sigma algebra containing only the empty set and the sample space, and it is not the power set. You know, it's not the collection of subsets that is basically exhaustive. It takes every subset. This one, it's phi and a and b, c, d, and omega. So is this a sigma algebra? Yes, you can verify that it has the properties of a sigma algebra. The empty set is there. If something is here, you will find its complement. The empty set is here, and here is omega. If this is here, which is the set only one, remember that omega is A, B, C, and D, so the complement of this subset is the other guys, B, C, D. It's there, here, it's this one. And the complement of this one is this one. So every subset and its if there is a subset here, its complement is indeed there. What else? Unions. Okay, so if you take the union of these two guys, you get big omega, it's here. If you take the union of anything with big omega, it is big omega, and it is there. Intersections, if you take the intersection of any of those guys and let's say phi, you will get phi, and it is there, and so on. Everything that characterizes a sigma algebra is satisfied, and so this is a sigma algebra. So see, so those are basically, three examples of sigma algebras. This example, this is very important, like to have, to have an idea what sigma algebra is. So you have a set which is big omega, and in probability big omega, it's not just an abstract set, it's basically a set that contains the possible outcomes of a random experiment. This set can be finite, can be countably infinite or uncountably infinite, okay? And here our example. The union of phi and A, okay, so that's a question. So phi union anything will be this thing itself. So phi union A is A, right? That's the union, and it is there, okay? And phi union BCD is BCD, and so it is there, okay? So everything is there. Now, the question, and you may say, oh, yeah, okay, so now you are choosing some subsets, okay? And if you go for F3, you are excluding some subsets. But why? I mean, why we are complicating the story? I mean, so omega contains all possible outcomes, okay? Why not just use all subsets of big omega? So just take the power set, that's it. I mean, why should we do a selection? What will force us to do a selection in the first place? It seems like we are complicating things, but, we need to do so. So the problem is when omega is uncountably infinite. Okay, so if omega is uncountably infinite, we will not be able to choose the power set. Why? We will tell this story later. Okay, so again, your intuition, basically anyone, not knowing this story will say, let's just take the power set, use all subsets. What I mean, so, take all subsets. If we do not use any, I mean, they will not harm us if we include them. They will not harm us, just keep them. But the problem is that when big omega is uncountably infinite, okay, this will not be possible mathematically, and we will show this. If omega is finite, if omega is countably infinite, yes, you can use the power set, and in fact, this is what we will do. But if omega is uncountably infinite, for example, if omega is the interval from 0 to 1, then surprisingly, there will be troubles if we try to use all subsets, okay? An example of a sigma algebra, the proof of this is in the notes. I will just, explain the example because actually it's very related to random variables. So this is very related to the concept of a random variable. So it's called the pre-image sigma algebra. Here is the story. So you have two sets, x and x prime. Okay, so you have two sets. And then there is a function, a map between these two sets. okay? And then there is a subset here called, let's say, y prime, and it has a pre-image. So what is a pre-image? If you don't know this term here, the pre-image is basically the subset of x that is mapped by our map or our function to this y prime. So the pre-image of y prime is y, okay? So this is the formal definition. What is y? It's all elements in big X that are mapped by the function to this y prime. So this thing is called the pre-image of y prime under G, under the map G or the function G. Okay, so now suppose that you define a sigma algebra on X prime. You know, or someone tell you this is a sigma algebra on X prime. So what do I mean now? So now you understand the term. So what is a sigma algebra? A collection of subsets of X prime that satisfies three things. Empty set is included. If subset A is included, then so is its complement. And if A1, A2, A3, and A4 and so on are included, then their countable union is included. So that's a sigma algebra. Now suppose that again you define a sigma algebra on X prime. So it is a collection of subsets of X prime. Now for each one of those subsets in the sigma algebra, go and obtain the pre-image in X. So each subset in X prime, it has a pre-image. Those basically elements in X that are mapped to the specific subset of X prime we are talking about. So for each subset in the sigma algebra on X prime, find the pre-image. So you will obtain a collection of pre-images. You can prove that the collection of pre-images, which is a collection of subsets of X, is in fact a sigma algebra on X. Okay? So again, you have basically X prime and X. You define a sigma algebra on X prime, which means that you choose a collection of subsets, you know, of X prime, subsets that are basically, that obey certain rules. I mean, simply this collection is not constructed in an arbitrary way. So if you construct a sigma algebra on X prime, now for each of those subsets, you find its pre-image. Okay? So you will get a collection of pre-images, and pre-images are basically subsets of X. The collection of pre-images, okay, is a sigma algebra on X. And in the notes on Blackboard, I mean, it's optional. You can, if you are interested, you can read the full proof why actually the pre-image collection is indeed a sigma algebra on X. Okay, but this will help us like later in the course when we talk about basically the definition of a random variable. Okay. So now what about a probability space? So that's the third component. The third component that we have. Okay. So if you take omega and the sigma algebra defined on omega, this is called a measurable space. A measurable space. Okay. Now you can add a third component to get a probability space, and this third component is called the probability measure. And the probability measure is a special case of something called a measure. Okay, so basically here probability is like sort of a special case of something bigger called a measure. And hence you can think of probability theory as a subset of something called measure theory. Okay, so again, I mean, before going into the probability measure, our heroes now are omega, sample space. It's basically a set containing the outcomes, all possible outcomes of a random experiment. Like if you if you roll basically a dice, so this will be 1, 2, 3, 4, 5, 6. Basically, if you choose a number randomly on the interval from 0 to 1, then it will be a real number from 0 to 1, and so on. So this will be omega. Then we have the sigma algebra thing, which is omega. It has subsets, okay? And so you choose to deal with some of the subsets of big omega. Under some circumstances, you can basically take all the subsets and use the power set of omega, but there are cases in which you will have to do a selection. This selection is not arbitrary. It must include the empty set. It must be closed under complementation and finite and countably infinite unions. Okay. Now you add a third component with it is a probability measure. So the probability measure is a function or a map defined on the sigma algebra. So basically, the domain of this function are those subsets of big omega that you have included in the sigma algebra. So basically, you assign included in the sigma algebra, you assign a number, and this number is from 0 to infinity included. Now this is generally a measure, okay? So you actually allow positive infinity, but we will not, for a probability, you will see later that we do not allow this. But again, if you have just a measure, not a probability measure, you can actually assign plus infinity. But for probabilities, we will not do so, okay? So here is the rule for having a probability measure. Now, every sigma algebra, it contains the empty set, right? So what is the number that we assign to the empty set? We must assign 0. You cannot do anything else. You must assign a 0 to the empty set. And to big omega, you must assign 1. Okay? To big omega, you must assign 1. Okay? And so this will basically impose the fact that you never use numbers actually greater than 1 in probability. But for general measures, you can use numbers greater than 1. In fact, you can use plus infinity. Okay? So again, in your collection of subsets, you assign the number 0 to the empty set, the number 1 to big omega, and now if you have subsets in the sigma algebra that are disjoint, this is very important. Those subsets must be disjoint, so their intersection, the intersection of any two of those guys. So if you take AI intersection AJ, this is the empty set for every I not equal to J. So the intersection should be 5, so that your basically subsets are disjoint. Then you must assign to the union. So what is the value that you assign to the union? It's basically the sum of the values that you assign to each one of those guys. Okay, so this is the third rule, so that you have something called a probability measure. Okay, and when we talk later about the properties of the probability measure, okay, to make sense, I mean, you may wonder about why those guys actually they make probability meaningful. Okay, so let's take an example. Okay, so here is big omega. Here is big omega, and big omega is equal to A, B, and C. So it is a finite set with 3 elements, and basically the power set it has 8 elements. Basically we have 8 subsets of big omega: the empty set, the set containing A alone, B alone, C alone, A and B, B and C, A and C, and ABC. Okay, and let's choose the power set to be our sigma algebra. Okay, again, if your omega is finite or countably infinite, in fact, it is recommended that you basically choose the power set as your sigma algebra, and you don't bother about selecting some subsets and discarding others. But it will not work if omega is, for example, the closed interval from 0 to 1. Okay, so here, because our sample space is finite, we can take as our sigma algebra the power set, and so those are basically the subsets in our sigma algebra, and those are all possible subsets of big omega. So what is a probability measure? A probability measure is a map. It's a function that assigns a number to each one of those guys. Guess what? This number is what we will later call probability. Okay, so this is a number that is assigned to each one of those guys. Now, is this assignment arbitrary? So can we assign any number to any subset? No. Okay, we assign non-negative numbers. We assign non-negative numbers. We never assign negative numbers. Okay, so this is number one. We assign basically, or we map the empty set, it's mapped to 0. And we have no option. If you want to have a probability measure, you have to do this. And omega itself, which is this guy, must be mapped to 1. Okay, so empty set is mapped to 0. The set itself is mapped to 1. And then we assign non-negative numbers between 0 and 1 to the other guys. But we cannot do so in an arbitrary way. There is a third thing here that is very important for a probability measure to make sense. And this is that you must assign to the union of disjoint subsets of big omega, you must assign to the union the sum of the probability values assigned to each individual subset. So let's see what I mean here. So let's say that you take A and you assign it to 1 over 4. And you take B and assign it to 1 over 4, right? So this is sort of arbitrary. However, if you do so, set A intersection set B is the empty set. So basically these two sets, they are disjoint. So they are disjoint. So according to this rule, you are under obligation. Now, if you take the probability of A union B, which is what you assign to the subset A comma B, now you are not free to assign any number that you wish. You are under obligation to put here the sum of these two guys. Okay, so if this is 1/4, this is 1/4, then you must take AB and assign it to 2/4, which is 1/2. Okay, so this is, this is basically the third requirement, that if you assign basically numbers, so say, okay, B of A1 is something, B of A2 is something, B of A3 is something, then what is B of A1 union A2 union A3? What should be this one? Now, if those guys are disjoint, this is very important. If they are not disjoint, this is not, what the probability measure is about. If those guys are disjoint, then you need to assign the sum. Okay? So, provided that those guys must be disjoint. Okay, and again, when maybe in a lecture or two, we will, when we talk like, here we are very abstract, but when we talk about, probability in like, in a way that is more close to reality, basically, we will see why these properties are very important. Okay, so let's give an example, and this is a probability measure that, again, I mean, if you read, I mean, you will not have a sense that this is like probability as you know it from a previous course or from basically something you know about probabilities from your previous life. But again, it's like, formally speaking, probability is abstract like this. You just define things in a very specific way. Now let's see that if I take omega and a sigma algebra, now let's take an element in the sigma algebra. So basically this is element, an element in big omega in the sample space, which I will denote here as small x. Now, here is how we will define our probability measure. Okay, so our probability measure, we will take a subset in the sigma algebra, which is the collection of subsets of big omega that includes the empty set and that is closed under complementation and finite and countably infinite unions. We will take basically this subset and we will assign to it a number. This number is non-negative, and basically we will examine whether small x, so small x is fixed, it's a number, you know, we will choose a particular x from big omega. If small x is in A, is in this subset, we will assign to this subset the number 1, and if small x is not in the subset, we will assign to A the number 0. And I claim that basically if you do this to every subset in your sigma algebra, then you indeed have a probability measure. As defined. So how can we check that something is a probability measure? You need to basically check whether those are satisfied or not. Don't think too much about the meaning for now. Just follow your nose and check the definition. You know, if basically everything is checked, that's it. Then you have a probability measure. So again, someone said, you know, I will take each subset in the sigma algebra. If x, which is some particular element of interest in omega, if it's in the subset, I will assign 1 to it. If it's not, I will assign 0. Is this a probability measure? Okay. So what is the number assigned to the empty set? So the empty set is guaranteed to be in the sigma algebra by construction. So what is the relationship between element x and the empty set? Well, nothing belongs to the empty set. So according to our assignment rule, then the empty set will be assigned 0 because x is not in the empty set. Okay, and so this is the first guy here. It's okay. So according to our rule here, yes, we assign the empty set to 0. What about big omega? So what is the relationship between x and big omega? Well, x is an element in big omega. Okay, and so according to our assignment rule, we will give big omega 1, which is needed to have a probability measure. Now the challenge is the third property satisfied. Okay, so let's consider disjoint sets A1, A2, A3, and so on. And now we need to compare, right? So we need to take basically A1, A2, those are disjoint. Okay, disjoint, and of course all of them are in the sigma algebra, and we need to compare two quantities. Okay, so what do we give to the union? And okay, of those disjoint sets, and the sum of what we assign to each one of those guys. Now, to have a probability measure, these two quantities must be equal. If they are not equal, then we don't have a probability measure. They need to be equal. Okay? So you choose X. Now, we have two possibilities, two cases, okay? So case 1, or case I, that X is in the union. Okay? So it may happen, we don't know specifically what those guys are, so we will need to investigate both possibilities, that X is in the union or X is not in the union. Now, okay, so if X is in the union, then what is this quantity? According to how we define this function, mu, we define it in a very specific way. We say that we pick a subset that is in the sigma algebra. We examine whether small x is in this subset or not. If it is, we assign 1. If it is not, we assign 0. Under our assumption, x is in the union, so now this guy here will be equal to 1. Okay? Okay, what about the sum? What about the sum? Note that, I mean, can we say what are those guys? So here is the reason. Now, if there is an element x that belongs to a union, what does this mean? What does it mean to belong to a union? It means that x is a member of some of those guys, right? So being in the union means there exists some m such that x belongs to am, right? Because if x is not in any, then it is not in the union. Okay? So x is in some am. Now, if x is in the union, in a general union, then it may belong to one of those a's or more. But those a's are not anything. They are disjoint, which means that if there is an x in am, then it is not in any other a, because the a's are disjoint. So this means the following, that basically this summation here that we are investigating is equal to mu a1 plus mu a2 plus mu am minus 1 plus mu am plus mu am plus 1 and so on. Now, because x is in the union, then it is in one of the guys, let's say am. So this guy here is equal to 1. But because the a's are disjoint, then if x is in am, it cannot be in any other a. So automatically x is not in a1, it is not in a2, and according to our assignment here, if you are not in a, then you are assigned 0. So basically those mu's here will be 0, this one will be 0, 0, and so on. So basically in this summation, one element will be equal to 1 and all others will be equal to 0. So this summation is equal to 1. Equality. But we are not done yet. We are not done yet because we did this calculation assuming that x is in the union. So we need now to investigate case 2. Case 2. X is not in the union of AI. Okay? So, according to the assignment rule, if x is not in something, then you assign 0 or 1, you assign 0. So this becomes 0. Okay? What about the summation? Summation of mu AI. Okay, I is a natural number. Well, if x is not in the union, then x is not in any AI for every I. This is the definition actually. So basically, to belong to a union, then it means that you are in at least one. To not be in the union, it means that basically X is not in any. It's not in any. So this means that mu of A1 is equal to 0, mu of A2 is equal to 0, mu of A3 is equal to 0, and so on and so forth. So basically the summation is 0 plus 0 plus 0 plus 0 and so on. So this is also 0, and we have equality. And these are the two possible cases, nothing else. Either X is in the union or it is not in the union. Okay? So under both cases, basically, we have an equality between these two quantities, and this is what is needed to establish that we are dealing with the so-called probability measure. So the probability measure again, the probability measure is basically a function that assigns a non-negative number to each subset in the sigma algebra. You should assign 0 to the empty set, assign 1 to big omega, and if you assign basically numbers, so if you assign, you go here, if you assign numbers to A's that are disjoint, then the sum of those assigned numbers must be assigned to the union of them, whether this union is finite or countably infinite. If those are all satisfied, then we have a probability measure. Why did we not assign C to 1 over 4? Okay, so that's a good question. So if we say that this is 1 over 4, this is 1 over 4, this is 1 over 4, right? Then basically the assignment that we give to their union. So what is the union of A and B and C? They are disjoint, right? So basically if you give A union B union C, then this is what you assign to ABC. Okay, so according to the third property, the third one, if you have disjoint sets, you need to assign the sum. So I should assign basically the number given to A plus that given to B plus that given to C, and so this will be 1/4 plus 1/4 plus 1/4, which is 3/4. Okay, but we have a problem here, because basically the union of these three guys is big omega in our case. Okay, but we should have of big omega, which is A, B, C, I mean in our case, equal to 1. That's the second property of a probability measure. So that's a very good question, because it will tell you that the assignment of probabilities is not arbitrary, right? So now, if you assign 1/4 to A, 1/4 to B, you are under obligation to assign 1/2 to C, right? So that the probability assigned to their union is 1/4 plus 1/4 plus 1/2, which is 1. Because their union is basically big omega, you need to assign 1 to big omega. Okay? So if you assign A and B to 1/4, that's it for you. You cannot assign to C except the number 1 over 2, 1/2 or 2/4. And if you assign 1/4 to A and 1/4 to B, also A, B, the subset here must be assigned 1/4 plus 1/4, which is basically 1/2. Okay, so the assignments are not arbitrary at all, and they should obey these properties so that probability makes sense, as we will see later.